Hello everyone. So welcome to lecture 1 of Organic Chemistry 1. So in this lecture we'll review the concepts of general chemistry just so that you can go back to general chemistry and then just review the entire topic. So in this topic we'll discuss electrons, bonds, and we'll also discuss some of the molecular properties, and we'll also see introduction to organic chemistry. So in this chapter, this is the lecture outline. So we are going to first discuss the introduction to organic chemistry. Then we'll see the structural theory of matter, how matter is organized in terms of its structure. And we'll see what are the electrons, bonds, and Lewis structure. And we'll also see one of the most important topics in organic chemistry, identifying formal charge. And next we'll see induction and polar covalent bonds. And we'll complete it with atomic orbitals. And finally, in the first lecture we'll try to complete until valence bond theory. After that we'll continue with more molecular orbital theory, hybridized atomic orbitals. These are things that you've already learned in general chemistry, so we'll just review them here again. So next we'll talk about intermolecular forces and the physical properties of matter, and finally we'll discuss solubility. Now, so let's start with the first part, introduction. So what is organic chemistry? So the name itself says organic, meaning that it's the study of carbon containing molecules and their reactions. So what are we concerned about in organic chemistry is to remember that what happens to a molecule during a reaction. So first thing that happens is that one, the molecules collide, and number two, there are bonds that are broken, and then there are bonds that are made. So for example, if you look at an OH molecule here that's combining with the CH3I, so notice the movement of these electrons. Once they bump, they're going to exchange these electrons, and the change of these electronic structures is what results in a final compound. But why do we need to, why does these reactions occur? So these are things that you have already learned in general chemistry, but we'll try to focus just on the electrons in organic chemistry. So most of the entire organic chemistry focuses on the electron movement. So we'll focus on electron movement. Now, why do we distinguish between organic and inorganic compounds? Number one, inorganic compounds are separate. The only way is because organic compounds are ones that contain organic carbon molecules or carbon atoms. And organic, why do we need to study this separately? Is because organic compounds make up most of the things that we know and live with. For example, food, clothes, pharmaceuticals, plastics, all of these are things that we generally see in organic as a form of an organic molecule. For example, if you take a common compound known as ammonium cyanide, if you heat it up, you end up with urea, which is an organic molecule. So there are changes where you can make an organic molecule out of an inorganic molecule. Now, carbon compounds are also ubiquitous. Ubiquitous meaning that they are everywhere. So what are those compounds? So one of those compounds is rofec oxide. So this is a compound that generally used as a non-steroidal anti-inflammatory drug. The other one is atorvastatin. So the common name is Lipitor. So this is a pharmaceutical drug that's used to reduce the chance of having a heart stroke in really bad patients where you have a high risk of heart stroke. Next, you know already oxycodone. It's a opioid drug. So opioid drug that is generally used for severe pain. So atorvastatin and oxycodone are drugs that are generally used in osteoarthritis drugs. So these are painkillers, but there are chances that you might get addicted to them. The next common molecule that you already know is cholesterol. Cholesterol is a steroidal molecule, which is generally important for your body to produce vitamin A. It's also important for your body to produce vitamin D. There are many molecules that require cholesterol itself as the primary base source. For example, testosterone, estrogen, progesterone, all of these molecules are similar to cholesterol. So by changing the structure of cholesterol, we can produce all of those molecules. The next one is benzyl penicillin. So benzyl penicillin is a common antibiotic that is used for different conditions. So just search through and you can find many of them. Like this, there are many organic molecules, right? And most of the living things are generally made of organic chemicals. For example, if the proteins, so your hair and cell structures are made of proteins. The genetic makeup is made up of nucleic acids. The energy that you get is generally from carbohydrates and fats. and most of the medicines that we find are generally carbon compounds. So what makes carbon so special? If you look at it in the periodic table in period 2, you notice that there is lithium on one end and there is fluorine on the other end. But notice that all of the molecules before carbon are generally molecules that are ready to give up electrons. But all of the molecules after carbon are molecules that accept electrons. So carbon stays in between. So because it stays in between, it does not give up electrons, it does not accept electrons, but rather it shares electrons because of its ability to form bonds. This sharing is the reason why carbon has the best of covalent bonding. So the best of covalent bonding. So now let's talk about the structural theory of matter. So in mid 1800s, it was first suggested that the substances are generally defined by their arrangement. But why is this the case? Why is that you have a compound formula? Why not write a compound formula and get with it? Because there are chances that even if the formula is the same, so if you can have compounds that have the same molecular formula but might have a different structure. These molecules are called constitutional isomers. For example, if you take dimethyl ether and ethanol, if you look at the number of carbons, there are 2 carbons. If you look at the number of hydrogens, there are 6 hydrogens and there is 1 oxygen. Even though the molecular formula is the same, it can have the 2 similar structures with the same molecular formula. So because these are 2 separate structures with different bonds and different physical properties, we know that these are separate molecules with the same molecular formula. So these types of molecules are called constitutional isomers. So the atoms that are most commonly bonded to the carbon generally include nitrogen, oxygen, hydrogen and halides. So with some exceptions, each element generally forms a specific number of bonds. So for example, carbon is a tetravalent molecule. So the name itself says tetra, meaning that it can form 4 bonds. So there are trivalent molecules like nitrogen, which can form 3 bonds. Oxygen is a divalent molecule where it can form di representing 2 bonds. Monovalent molecules are hydrogen and halogens. These are molecules that can form only 1 bond. So what is covalent bonding? So we know that there is 2 types of bonding, ionic bonding and covalent bonding. Ionic bonding is where the bonding occurs due to the charge on the ions. The covalent bonding is due to sharing of pair of electrons. So it happens due to sharing of electrons. Why does this happen? So when you look at it in terms of a simple molecule, say hydrogen, so notice that as you decrease the distance between hydrogen to hydrogen, the more and more you bring together, you notice that they come close as much as possible, but at a certain distance. What happens here is that you have a hydrogen, 1 hydrogen and there is 2 hydrogens. As they come closer and closer, notice that there is a proton in the center with an electron in its outer orbital. There is a proton in the center and also an electron in its outer orbital. Protons actually repel each other, and also electrons repel each other. But a positive charge and a negative charge try to attract each other. And for this negative charge and positive charge also try to attract each other. When the repulsion of the similar charges becomes equal to the attraction, that distance between the 2 central molecules is called as the covalent length. And the molecules are said to be covalently bonded. So the molecules are said to be covalently bonded at that distance. For hydrogen and hydrogen, it's 0.74 angstroms, and the energy that requires you to bring those molecules that close is minus 436 kilojoule per mole. So when you break the molecules, they release energy. To form bonds, it generally has to absorb energy. So remember the idea. Here, to break it, it releases energy. When you have formed the bond, it absorbs energy. Now, what are the forces that are keeping them together? One is the attraction force between the positive charged nuclei and the negatively charged electrons. Second is the repulsive force between the 2 positive charged nuclei, repulsive force between the 2 negatively charged nuclei. So we already discussed this. Next, let's discuss the atomic structure. In general chemistry, we talked about two main structures inside a molecule. One is a proton, which has a positive charge, +1 charge, and a neutron, which is the neutral charge, and that generally resides inside the nucleus. So the first part completely resides only in the nucleus. Everything outside is just electrons. So the electrons have a negative charge and they reside in the orbitals outside the nucleus. Now, there are what we call valence electrons. The valence electrons are basically the electrons in the outermost shell. So basically think of them as the unfilled electrons. So they are not complete. So let's take a look at the carbon molecule. So which electrons are generally considered as valence electrons? So valence electrons are our focus here because these are the only ones that are involved in covalent bonding. So when you look at a periodic table, you can always calculate the number of valence electrons by analyzing the electronic configuration. So for example, group A elements, the group number represents the periodic, the number of valence electrons. So for group A elements only, in general, only 1A, 2A, 3A, 4A, 5A, 6A, 7A and 8A. Only these elements, the group number represents the number of valence electrons. Transition metals, it does not happen that way. So this is only for group number, is the number of valence electrons only for group A elements. Now, how to draw a simple Lewis structure? There are basically a series of steps that you can use to draw Lewis structures, which we already discussed in Inorganic 1. So Inorganic 1 and Inorganic 2. So I'll just review the case again. The first step is to draw the individual atoms using dots to represent the number of valence electrons, and put the atoms together so that they share pairs of electrons to make complete octets. For example, nitrogen is a 6A group element. For 5A group element, it has 5 electrons, and you have 3 hydrogens, and arrange them in an order where hydrogen shares each electron with nitrogen each, and basically they make a pair. Each pair represents a bond. Each pair represents a bond. So here there are 3 bonds. So for example, let's try drawing for CH2. So we know that carbon is a group 4 molecule, group 4A molecule. So it has 4 electrons. Hydrogens, there are 2 of them. So hydrogen and hydrogen. Oxygen it's a 6A group element. So number 1, number 2. Now let's start with carbon arrangement around the hydrogen first. So carbon with hydrogens. Now, oxygen now let's try and draw circles around the electrons that they are sharing. So you have, this is one pair between hydrogen and hydrogen, this is the other pair. But carbon here, with respect to the oxygen, it cannot just form one bond, but notice that it's still unfilled. So what happens here, rather than sharing one electron, they'll share 2 electrons. So they'll share 2 pairs of electrons. So the final molecule will look somewhat like this. So you have carbon, hydrogen, hydrogen with each pair around it, and there are 2 pairs of electrons between oxygen and carbon. So you can draw electrons or you can draw a single line. So this represents a bond, or you can replace it with a small dash that also can represent a bond. For example, in this structure we can also write this as C, bond H, double bond O. So this also represents a structure. Now remember that every molecule has shared electrons and unshared electrons. For example, here these 2 pairs are generally unshared pairs. All of the others, this and this, all of these are shared pairs. So remember this shared pairs and unshared pairs because we are going to come back to this again. So let's talk about formal charge. What is a formal charge? So recall the common terms that we used to use. So when you want to describe an unbalanced or a formal charge, so how do you represent them? An anion in general is a negatively charged atom. A cation is a positively charged atom. So whenever the atoms in molecules are typically neutral, so they can also be anionic or cationic. For example, even if they share electrons, they can also become anionic or cationic. So to determine the formal charge of an atom in a given molecule, so we generally compare the number of valence electrons that it owns and the number of valence electrons that the atom needs to be neutral. So that difference is what creates the formal charge. For example, let's take the molecule that we just talked about. So we talked about CH3O now. So this is a molecule. Consider the formal charge on the atoms in the structure below. So which one should it have? Should have a formal charge. Let's take a look at each of these molecules. Number 1, carbon. Carbon here has a total of 1, 2, 3, 4 valence electrons. So for it to be neutral, it needs 4 valence electrons. But in the bond, carbon is surrounded by 8 electrons. So but it owns only 4 of it. So then it gets only 1 from each of the bond. So because carbon owns 4 bonds and needs 4 electrons, so it does not have any formal charge. Remember that the number of the number of electrons that it has should be equal to the number of electrons that it should have, so it wants. So that represents a formal charge. Now let's take a look at the oxygen here. Oxygen originally has 6 valence electrons, but oxygen surrounded by 8 electrons. Notice here that this is 1, 2, 3 and the bond represents 4. So that's about 8 electrons. But originally, how many does it own here? So it only owns 7 of them, because notice that there are 2 electrons here, which means that only one of the electron is owned by the oxygen. So there is only 1 from the bond and it has 3 lone pairs. So the oxygen originally only owns 7 electrons, but its valency is only 6 electrons. So it has an extra electron. That extra electron represents a formal charge. So what we'll do now is basically write a minus on the oxygen. So that minus represents that it has more than what it wants. So that's how we can say that it has excess. Now, if it has more than its valency, the formal charge is negative. If it has less than its valency, the formal charge is positive. So for example, one way of looking at this is, notice that the valency of oxygen is 6 electrons, but how many electrons does it have here? With considering the sharing part, it has 7 of them. So there are originally 6, but it has 7. So you can write 6 minus 7. That becomes minus 1. So the oxygen has a negative formal charge. So try other molecules. For example, try another molecule, say I'm going to write a molecule of ozone. So try this as an example and try to find out its formal charge. Next, let's talk about polar covalent bonds. So we talked about covalent bonds. Let's talk about polar covalent bonds. So before talking about polar covalent bonds, let's talk about electronegativity. So electronegativity represents how strong an atom attracts the shared electrons towards itself. So if you look at it in the periodic table, as you go along the period, it increases the electronegativity. As you go down the group, it decreases the electronegativity, but as you go up the group, you also increase the electronegativity. So one of the molecules that has the highest most electronegative atom is fluorine. So then you can always remember that the relative electronegativity of the atom in the same column of the same row of the periodic table. There are generally 3 types of bonds. One is what we call a covalent bond, the other is a polar covalent bond, and finally the last one is called as a ionic bond. How do we differentiate this between the bonds in terms of a number? We differentiate them based on the difference of electronegativity between the atoms. For example, if there is carbon and carbon, we are talking about 2 atoms that have a different electronegativity, so each of them have their own electronegativity, and we want to find the difference between their electronegativity. That value is what we are talking about. If this difference in electronegativity is less than 0.5, those types of bonds are called covalent bonds. If this electronegativity value, difference in electronegativity, is between 0.1, 0.5 and 1.7, we can call this a polar covalent bond. And if the difference in electronegativity is greater than 1.7, we can call this an ionic bond. So this is how we can find the electron based on the electronegativities. We can write what type of bond the molecules have. The difference here is that covalent bonds, whenever they have the electron share, each of them share their electrons equally, meaning that if they have two electrons between them, both of them have one each. But when you have a polar covalent, let's talk about ionic bond. In an ionic bond, they split, but rather than sharing electrons, they undergo a transfer of electrons. So they transfer electrons for them to form a bond. Then what is a polar covalent bond? Polar covalent bond is where there is a partial sharing, which means that the molecule, so the atom with higher electronegativity, so drags the electrons towards itself, causing it to have a partial negative charge, and the molecule that has lesser electronegativity, so this has the higher electronegativity, this has the lesser electronegativity. So the one with the higher electronegativity gets a partial negative charge, and the one with the lower electronegativity gets a partial positive charge. These types of bond are called as a polar covalent bond. Now, in polar covalent bonds, electrons tend to shift away from the lower electronegativity atoms to the higher electronegativity atoms. This property can be represented by an arrow with a plus in the start. This is one another way of representing that the charge. So the arrow always points towards the molecule with the higher electronegativity, and the arrow starts at the molecule with the lower electronegativity. So this is one way of representing it. It's not always true that a molecule should have a specific electronegativity. Remember that we are talking about two molecules and the difference in electronegativity. So whenever we say something is low, we are comparing it to the high. Whenever something we are saying is high, it means we are comparing it to the low. For example, if you take the same molecule with carbon and lithium, carbon will have a partial negative charge and a lithium will have a partial positive charge, because in comparison, carbon has more electronegativity than lithium. So the greater the difference in electronegativity, the more polar the bond. So as you start at the covalent structures, for example, C bond C to C bond H, you get a polar covalent structure from nitrogen hydrogen, carbon oxygen, lithium carbon, lithium nitrogen, and then you enter the structure of ionic, which is NaCl. So you start with a really small difference in electronegativity to end up with a large difference in electronegativity. Now, polar covalent bonds, in some bonds that are acceptable, you can write them as a covalent bond or an ionic bond. For example, carbon lithium can be written as a covalent bond or an ionic bond. So the electronegativity difference here is 1.5. So it is on the cusp of polar covalent and ionic. So according to just one method, we use this. So the absolute difference in electronegativity, so we cannot, we have to take it to be with a grain of salt.